Again, welcome to Biostatistics. In these lectures, we're going to study about one-way ANOVA. Again, the main reason why we are using one-way ANOVA is when we have more than two samples to compare or more than two populations. So for example, if I have three groups of some samples or population and I want to do hypothesis testing to compare their means or any characteristics to compare, most likely I'll use one-way ANOVA. Again, there are other techniques that we can use, again, when we have more than two groups. So in these lectures, we're going to learn the concept of descriptive statistics. For example, when we want to do data analysis, the first thing we may do is exploratory data analysis, which is trying to understand our data. So maybe we may find the mean, median, mode, variance to find how the data is varies, the positions of the data, finding the quartiles. So here we're going to do some few descriptive statistics concepts. Then we start with the problem of multiple comparisons. Here we are talking about when we have more than two groups. We did t-testing when we have two groups. And then we move on to analysis of variance, which is one of the techniques we can use to test three or more groups. Then we look at post hoc comparisons and then the equal variance assumptions. So we start with an example, and this example again is from our course textbook. This is Biostatistics PH 661 class. So this example is, we want to know if pets as moderators of a stress response. So we want to know if pets can reduce a stress response. So here we have three groups. The first group, we monitor the group with the presence of a pet dog. Second group, we monitor the group in the presence of human friend. Then the third group, we monitor with neither a dog nor a human friend present. So here again, we are going to do the stress test comparison of the three different groups. So the best testing method we're going to use here is the ANOVA. So let's start with the question. Here said this chapter follows the analysis of data from a study in which heart rate, BPM of a participants were monitored after being exposed to psychological stressor. So participants were randomized to one of the three groups. We have group one, monitor in presence of pet dog. So we have these groups again exposed to a stress condition or psychological stressor. Now, most likely, if they are with their pet, maybe the stress will be lesser. When they are with their friends, maybe the stress will be lesser or more. And also maybe when they are not with friends nor dog, they are alone, the stress may be different. So here we have three different groups and we want to compare the stress conditions, the stress level based on three different conditions. So this is our data set. We have group one when the pet is present. This is the sample and this is the rate, the values for the BPM. Then we have group two when friend is present. This is also the values for the BPM. Then we have group three when there is no dog and there's no friend available and we have their values. So here we want to compare these three groups. Which group have less stress based on their blood pressure measurement, the BPM. So here we're going to use SPSS application. So most computer programs require data in two columns. So here we're going to have one column for the group, which will be our explanatory variable, the group, other group 1, 2, 3. Then another column is for the response variable, which is the heart rate, the BPM. So this is SPSS. We have our group, 3 different groups, 1, 2. So in the group section, only 3 possible values we can have. Then we have the heart rate for each person. So again, we can use SPSS to analyze this data, compare the 3 groups using the ANOVA. So the descriptive statistics we want to do here is that we want to find the values that we have is for each individual. So let's find the average measure heart rate for all the 3 groups individually. Then we can even from there see that, okay, group 1 have the highest average rate than group 2. So most likely group 1 have more stress than group 2. So we took the first data. Again, the sample size is 15 for all the 3 groups. The mean for the heart rate, we can see that group 1 is very good when the pet is present. We have 73.4831. Group 2, when the friends is present, is very high, 91.3251. Then group 3, neither pet nor friend, we have 82.5241. So the total here we get, total we have 45. And also the total here, which is 82.4441, is the average of the 3 groups together. And the same thing, average of the 3, this will be the standard deviation. So we can see how the data disperse. So exploring the group differences, John Tukey taught us the concept or the importance of EDA, which is the exploratory data analysis. So we can use something like a Stemplots, box plot, or dot plot to visualize our data. In this example, we use the Stemplots. So we can see the Stemplots of the first group, the second group, the third group. So just by looking at the Stemplots of the first group on the left, I can see that it's close to normal curve, the best shape, but not really. When I look at the second, which is when the friends are present, we can say that it's like a skew to the left or negative skew, which means the mean will be lesser than the median. But we can see that to the left and the top, the lower part is very slim tail. And the right part, the highest value is very, so this is negative skew or skew to the left. Then neither friend nor pet present also look like a normal curve also. Actually, that look more like a normal curve distribution than the pet present. So here we are doing what we call the exploratory data analysis. We try to understand the individual data first before we do our comparison. So descriptive statistics is the best way to understand your data, to summarize your data. We can find the mean, median, mode, use the box plot, or use the Stemplots or dot plot to visualize your data. In a Stemplots, we can visualize the data by location, the percentage location. Let's say Q1 is 25%, Q2 is 50%, and the box go up, we know that we have higher values. The box is down means we have lower values, etc. So actually we have the box plot here for the 3 groups. So we can say again, the sample size is 15 for each group. The pet, we can see that the box is down, which is very good, which means, again, here is a heart rate. So the heart rate, the higher your heart rate means your heart beat faster, which is not good. That means you are more stressful. So we can see that with pet, your heart rate is low. I mean, it's not too high. So your stress is a little bit down. Comparing to with a friend or control. Control means there's no pet, no friend. So I would say with a pet is better. And then the second better one would be without a pet and without a friend. But with a friend, again, maybe due to friendship, understanding, concept, for some reason with friends, the stress went up. So now we finish with the exploratory data analysis. Again, analyze your data is up to you, but descriptive statistics is the best. I would say here we can see the example here. We don't need the media, really, we don't need the mode, but we need a mean so that we see the average of the stress level for the three groups. That can even give us the good idea of what we are coming to do. And the standard deviation is important so that we know how the data varies. Is there big difference? Now, when we look at the three groups, we can see that the standard deviation, the values are very close. I think somewhere between 8 to 11 or 9 to 11. So it seems like it's not that bad. And also, we don't need a variance. But box plot maybe is good. It's up again, when you're analyzing your data, it's up to you what part of the data you want to understand. Somebody may come up with the quotas to see the 75% distribution, up or lower, 25%, etc. So now we finish up with our descriptive statistics to understand the data. We are going to start with the hypothesis. Now, we said here that consider a comparison of three groups. There are three possible t-tests when considering three groups. Because now we can say, okay, in a HO, M1 equal to M2. This is for three groups, and we can also say M1 equal to M3 or M2 equal to M3. Now, if we want to do one, we can also say M1 or mu1 equal to mu2 equal to mu3. Then you can say the alternative hypothesis can be only one. Mu1 not equal to mu2, or mu3 not equal to mu2 or mu1. Because the null hypothesis said all the three are the same. So HA, all you have to say is that at least one of them are not the same with the rest of the two. Even if two are the same and one is not the same, it's still against the HA. But here we break it down that we have three possible t-tests. We can have M1 equal to M2, or M1 equal to M3, or M2 equal to M3. Now, if we say mu2 equal to mu3, then our HA will be mu2 not equal to mu3. We say mu1 equal to mu3, then our HA will be mu1 not equal to mu3. Or we say mu1 equal to mu2, then HA will be mu1 not equal to mu. Always, as we know from beginning, hypothesis testing, HA always go against HO. HO, which is the null hypothesis, is our claim. We also said that, however, we do not perform separate t-tests without modification. This will identify too many random differences. The most best way to do it, I would just say HO is M1 equal to M2 equal to M3, and HA is M1 not equal to M2 not equal to M3, or M1 not equal to M2. Then from there we start our steps. So here we see the problem of multiple comparisons. See, here we have three different comparisons to make. It's what we call the family-wise error rate. A family-wise error rate is the probability of at least one false rejection of HO. One false rejection of HO. So here we say assuming three null hypotheses are true. If all the three null hypotheses are true at alpha equal to 5%, then the probability of retaining all three HOs will be 1 minus 0.05 to the power 3, because alpha is again 0.05. So if all the three possible HOs are true, then probability of retaining all the three HOs will be 1 minus the alpha value to the power 3, which will give us 0.857. So therefore we say that the probability of rejecting at least one will be 1 minus 0.847. Should be 0.857 again. So the answer will be 0.143. This is what we call the family-wise error rate. Because we can see that here we say family-wise error rate is much greater than the intended. This is the problem of multiple comparisons. You can see the alpha is 0.05, but the probability of rejecting at least one will be 1 minus 0.847, which will give me 0.143. 0.847, again, as I said, 1 minus 0.05 to the power 3 should give us 0.847. And that's the values here. So now, problem with the multiple comparison, as we said, the more comparison you make, the greater the family-wise error rate. Because when we make more comparison, what happens? The value here will be decreasing. Because let's say 1 minus 0.05 to the power 3, you get 0.95 to the power 3, we get 0.847 or 857. Now, if we are doing 10 comparison, then it will be 0.95 to the power 10, which will be lesser. So if it's lesser than 0.857, now the probability of rejecting at least one will be higher because we get 1 minus a less value than 0.847. So our answer here will be the probability of rejecting at least one will be higher. So that's the main concern we are saying here. The more comparison you make, the greater the family-wise error rate. So this table demonstrates the magnitude of the problem. You can see that when we have only 2, number of groups is 2, the number of pairwise is 1 comparison. Because if I have 2, only 1 comparison I will make. It's 2 groups, mu1 equal to mu2, so mu1 not equal to mu2. But when I have 3 groups, I can make 3 different comparisons, as we saw. So when we have 3 groups, we can make up to 3 comparisons. And the probability of at least p-value is less than 0.005 is here to be 0.143. Here is where we get the 1 minus 0.05 to the power, whatever the number here, the power is 3. So 3, the answer you get, and this is what I'm trying to say. You say here we have 0.05, the alpha. We have 3 different groups, so it's 1 minus 0.0, and that gives us, the answer we get, we subtract it from 1, and that will give us the probability of rejecting at least 1. And that's what we are, that's the values here. So for example, let's say we have 8 groups. The number of comparison will be 8. I mean, the pairwise comparison will be 28. We have 8 groups, so 28. Now, if it's 28, I'll find the first probability will be 1 minus 0.05 to the power, again, 8. The answer you get will be what we have here, 0.762. Now, subtract 0.762 from 1, which will be the probability of rejecting HU. You can see that now it's high. So, but previously, when it's 3 group, it was 0.14 something. Now we are looking at 0.2 something, 24, 238 something. So that's the problem of multiple comparison. The more comparison you make, the higher the probability of rejecting HU is. So mitigating the problem of multiple comparison, we use what we call the 2-step approach. We're going to test for the overall significance using a technique called the Analysis of Variance. So this is where ANOVA comes in. So we always say that when we have to compare more than 2 groups, at least 3 or more, instead of using the t-test because of the family-wise problem, we may use, again, ANOVA can solve the problem. So the family-wise error rate is high when the number of comparison is very high. Or we can do what we call the post hoc comparison on individual groups. So we start with the analysis of variance. There are some conditions we have to meet here. Here we are doing one-way analysis of variance. We say the categorical explanatory variable, the response variable will be quantitative. Also, the test group means for a significant difference. So we have to have our explanatory variable. Sometimes we use the term independent variable will be the categorical or input variable. Then the output or dependent will be, which is the response variable, will be quantitative. So doing the hypothesis here, we can say the HO, you can see that here we are not doing multiple comparison no more. We say HO is mu1 equal to mu2 equal to all the way to mu k. K is the number of groups. So if we have 3 groups, then it will be mu1 equal to mu2 equal to mu3. Instead of saying mu1 equal to, because when you are doing 2 t-tests, you compare 2 groups at a time. So if my group is 3, I cannot compare all the 3 at the same time. I have to say mu1 equal to mu2, mu1 equal to mu3, mu2 equal to, so here I have 3 different comparisons. But with the ANOVA, we're going to say that mu1 equal to mu2 equal to all the, it depends the number of, let's say we have 3 groups, so we say mu1 equal to mu2 equal to mu3. Then the HA will be at least one of them is, one of the answers is different. So if we say mu1 equal to mu2 equal to mu3 equal to mu4, then we find out that mu3, 2, 3, 4 are the same, but it's different from mu1. So mu1 not equal to mu2, then we have HA. So HA will be at least one of the mu's, or the mean population mean should be different. So the method is to compare the variability. Actually, that's what we call the testing analysis of variance. We are going to use variance. So compare the variability between groups to variability within the groups. So here we have to use what we call the F statistics. We have the F statistics table. So when we are looking for the p-value, we go to the F table when we are using ANOVA or analysis of variance. So we'll see some form, we have to use some formulas here. There's a formula for between groups, within the groups, the mean square error, etc. So variability between groups, we are saying that the variability of group means around the grand mean. It will provide a signal of group difference. So variability of group means around the grand mean provide a signal of group differences. And this will be based on statistics we call the mean square between, MSB. So the notation we have SSB, which is the sum of square between. Then we have DFB. We know DF is degree of freedom, but this time degree of freedom between 2 or more groups. Then the K will be the number of groups. S bar is our grand mean. Then we have S bar 1, 2, etc., which will be the mean group. So if I have 3 groups, I can have the S bar 1, S bar 2, S bar 3 for all the 3 groups. So this is the formula for between, mean square between. The sum of square between groups will be the difference of each group mean minus the grand mean, all squared times the size of the sample. Then we add it to the next group. So the first bar will be the group. Let's say group 1 mean minus the total or grand mean of the whole groups times the sample size plus the mean of the second group minus the total grand mean times the sample again. So that's the formula here. And the sum depends, again, K is the number of groups. So if number of group is 5, then we're going to have 5 different sections. Then we had all the 5 values together. So the degree of freedom for between is still k minus 1. And this time the degree of freedom is not n minus 1, which is the sample size minus 1, but rather the number of groups minus 1. Then we also have the mean square between. So we have the sum of square between, degree of freedom between. Between means between two the groups. The mean square between, this is the formula here. Also, we have the sample size. Each group mean, or each group which will be the sample, so the sample mean group, minus the grand mean for the groups, plus the second group mean minus the grand mean times the sample size, plus the third group mean minus the grand total mean times the sample size. Then we add all together. Then we divide by the k minus 1, which is the group size minus 1. So if the group is 3, then we divide by 3 minus 1. So this is an example. The variability of group means around the grand mean. This is the basis of mean square between. So we have the pets and then stress illustrative data. So we can see our pets. Our pets mean is given to be 73.483. The grand total mean is 82.444. So how do we get 82.444? We had the S1 mean, which is the pet mean, plus the S2 mean, which is the friends group mean, plus S bar 3, which is neither friend nor pet mean. So here from this diagram, we can see the difference. The grand mean with the pets group mean, the difference was negative 8.9 to 961. Then the friend mean is high than the grand mean, so we get positive value. And also neither is almost the same, so we get 0.080. So the mean square between example is given here. How can we find it? Again, we are using the same data set for the pets, friend, no pets, no friend. So which means our K will be 3 groups. We know the mean and also the sample size is 15. So 15 times the pet mean is 73.483 minus the grand mean, which is 82.444, all square, plus the sample size times the second mean, which is 91325 minus the grand mean, which is again 82.444, plus the sample mean 82.524 minus 82.444 square. So we have 3 groups. We get all their mean, difference of their mean and the grand mean, then times the sample size. So after that, we had all the values and we do our arithmetic operation. We will get 2387.671. Degree of freedom, again, the group is 3. Pets, friends, no friends or no pets. So 3 groups. So degree of freedom between will be 3 minus 1, which give me 2. Then the mean square between will give us our SSB, which is the sum square between 2387.671. Then divided by degree of freedom between, which is 2. So that gives us 1193.836. So those are the ways of finding the between the group values. Sum square between, mean square between, etc. Next, we're going to also talk about within groups. So variability within groups. Here we say the variability of data points within groups can quantify the random noise. So based on statistics called the mean square within, where again this is MSW. Previously it was MSB, between and within. So these are the notation. The sum of square within will be SSW. Degree of freedom within will be DFW. Sample size, all groups combined, will be uppercase N, which means uppercase N means I have 3 groups. Each group sample size is 5. So uppercase N will be 15. 3 groups, 5 times 3, 15. And then we have the actual lowercase sample size, which depends on each group. Then we have also the variance of group. So this is also the formula for the mean square within. So the mean square within is normally SSW over degree of freedom W. Then the sum of square within will be the sum from one group to K groups, N1 to Ni, whatever the minus 1, times the variance of that group. So each group has its own variance value. Then degree of freedom in our group between, degree of freedom between, it was K minus 1. But here, degree of freedom within will be uppercase N minus lowercase k. Uppercase N minus lowercase k. So this is our, again, a plot again for our 3 groups. We can see that the mean for the pets is down. So that's why the plot is down. So this is the mean square within example. We find the sum square within, which will be 15 minus 1, 9.9698 square. Plus again 15 minus 1. And the mean the 8.3412 square. Again, we are using this formula here, SSW, N1 minus 1 times S square. So we get the 3 values, N minus 1, as we saw the formula here, N minus 1, and then the variance square. So after we get the SSW, you can find the degree of freedom W, or DFW, which will give me 45, because N minus 3, that will give me 42. Now, to find the MSW, again, it will be the SSW over DFW. We have the SSW to be 3561.316. We have DFW to be 42. So when we divide these 2 values, we get 84.793. Now we have to look for our table. So here we say we are using the F statistics and also ANOVA table. In this, the table data are arranged to form an ANOVA table. We have the between groups, sum of square, degree of freedom, the mean square. Then within groups, we have 4284.793. So the F statistics is the ratio of the MSB to MSW. So the F stat will be, give me the value I get for MSB, that's between, divided by MSW, which is mean square within. So the F value is 14.08. We have to go to the table to go and look for the corresponding P value. So here we say the F stat as a numerator and denominator degree of freedom. So we'll see the degree of freedom in 2 rows, respectively. So we convert the F star to p-value with a computer program or F distribution table. So let's see how the table look like. So this is a critical value for F2, 3 from table D. So here we have the value F 14.02. And we can see how the p-value illustrates down here. So when the p is less than 0.001, you can see that again. The rate is way down. So the ANOVA example, to summarize, this is ANOVA again is a hypothesis testing. So first we state our HO and our HA. When we are doing ANOVA, we compare everything once. So here we have mu1 equal to mu2 equal to mu3. Then HA will say at least one of them are not the same or they differ. So after we state our HO and HA, the next step is to do our test statistics. We need to find the F stat. So we saw the steps that in order to find the F stat, we have to know the MSW, MSB, SSB, SSW. We use the formula to find everything, then we get the F stat. When we get the F stat, we go to the F table to go and find the P corresponding value. So in this case, we use the computer application, and that gives us 0.00021. This will provide highly significant, because we can see the p-value is way very small comparing to the regular alpha 0.05. So we say we provide highly significant evidence against HO. Again, hypothesis testing the same. When p-value is less than alpha value or is very small, we have a strong evidence against HO. If p-value is greater or equal to the alpha value, then we have strong evidence to accept HO. We are not going to reject. We reject HO when the p is very small. So the significant level is an optional, but here we can set it to any amount. So this is the ANOVA table produced with SPSS for Windows. We see the pets and also the stress illustrative data. So we have between groups or within group and total. So the sum of square, we have the two groups values. And in terms of the degree of freedom, between groups, within groups is 42, total is 44. Then the mean square, we have the values for both between groups and within groups. So when we know but again, when you are using computer, we don't need the formula, everything will be given to us. So based on the values given, we're able to find the F to be 14.079. And based on this, we were able to find the p-value. Then here we say that ANOVA for two groups is equivalent to the equal variance pool t-test. So we normally use ANOVA for 3 or more groups. For 2 groups, it's almost same as using the t-test. So both address mu1 equal to mu2. Then the degree of freedom will be uppercase n minus 2. The MSW will be same as the variance. So S square pool, S square is the variance. So we have the F stat equal to T stat square. So we have F at 1, degree of freedom 2 alpha. And we're going to generate the result. So the next is the post hoc comparison. The ANOVA, we say the HA says at least one population may differ, but does not delineate which differ. It doesn't say whether mu1, mu2, mu3 or differ. Post hoc comparisons are pursued after rejection of ANOVA HO to delineate the differences. So for example, here we can use the SPSS, multiple comparison procedure variable in SPSS for Windows. So we use the least square distance, LSD, and also Bonferroni method will be covered in this section. So I use my SPSS to do so post hoc multiple comparison. I will select the LSD or the Bonferroni. Then the significant level, we select it 0.05. Then we click continue. Then we can get our result. Also, the least square difference procedure, we did hypothesis testing. Here they say we should do after a significant ANOVA is protected against problem of multiple comparison. So our HO will be mu I equal to mu J versus mu I not equal to mu J for each group I and J. Then we do our t-test. Here you see that we are doing two comparisons. So we do our t-test. And the t-test formula here we use to be the two groups, the difference of the two groups mean divided by standard error, the difference of the two. Now the standard error for the difference of the two groups is MSW 1 over NI plus 1 over NJ. That is the sample size for both groups. Then when we get a t value, then we go and get our p, then we make the decision. So this is example for LSD procedure. Here we say for the PET illustrative data, we test mu1 equal to mu2 by hand. The other test will be done by computer. That's mu2 equal to mu3, and also mu1 equal to mu3. So our hypothesis test is a mu1 equal to mu2 against mu1 not equal to mu2. So if we have the test statistics CFS, we find the standard. Again, here we are doing t-test, so we find the standard error. So we know this MSW over N and 1 over NI, or the N1 plus 1 over N2, we have two groups. So the sample size are the same. Plug in the value, we get the SE to be 3.362. Then we find the t-stat, which will be the difference of the sample groups divided by SE. So we compare, we put in all the values, do our arithmetic operation, we get negative 531. So here also we can graph. This is again using the SPSS for Windows. We can graph produced with SPSS for Windows, Chicago SPSS Incorporated, etc. So here we have the dependent variable heart rate, LSD. So we have the first group, which this will be our explanatory data. So we have 3 possible groups. Then we have their values. And we have the mean difference, the standard error, the significant level. We can find the lower bound, upper bound. So also here we can also find the confidence interval for ANOVA, and also the mean difference, and also LSD. So the confidence interval again will be 1 minus alpha times 100% of for the difference of the two group mean. So mu I minus mu J equal to the sample mean of the two groups difference plus or minus, we are using the t test, so it's to be t n minus k. N minus lowercase k is our degree of freedom value. So t will be n minus k, and then 1 minus alpha over 2. Then times MSW 1 over NI plus 1 over NJ. So let's do the example for 95% confidence interval for LSD method. So we know, we say 95% confidence interval, so our alpha will be 0.05. And this is for mu1 and mu2, so the difference of mu1 and mu2. So we find the sample of the two differences, the mean sample difference, plus or minus t, n minus k, 1 minus alpha over 2. These two values are very important, and n minus k is the row, which is the degree of freedom for the row. Then 1 minus alpha over 2 will be our p-value for column. So with if we know the column value and we know the row value, which is degree of freedom, we can find the t-value. Then we multiply the t-value by the MSW 1 over n1 plus 1 over n2. So here we plug in all the values. And at the end, we get the answer here. We also have the Bonferroni procedure. And here we say Bonferroni procedure is instituted by multiplying the p-value from the LSD procedure by the number of post hoc comparisons. So we have a hypothesis HO is mu1 equal to mu2 against mu1 not equal to mu2. The test statistics, we follow the same t-test, same as the LSD method. Then the p-value, the LSD method produces p, which is the two-tail, since there were 3 post hoc comparisons. So we can plug in the values for the confidence interval and same formula. We have negative 26.3 to negative 9.4. So this is the pattern and stress illustrative example. We plug in the values for the group and individual, and we can find everything. The next section is called the equal variance assumption. So conditions for ANOVA, first we have to make sure the sample is independency. So sampling independency. Also the normal sample distribution of mean. So the means should be normal distribution. Then equal variance within the population groups. So now let us focus on condition 3, which is the equal variance within the population groups, since condition 1 and 2 are covered elsewhere. So the equal variance is called the homoscedasticity. And also unequal variance is called the heteroscedasticity. Again, very hard to pronounce the two words. And this, the other one, allows us to pull group variances to form the MSW. So here we say the equal variance. The graphical exploration, we compare the spread visually with side-by-side plot. Then we do our descriptive statistics. If a group standard deviation is more than twice the other, be alerted to possible hetero S problem. And then the last step is do our test variances. Here we do our stat test, can be applied. And then we have the Levene test of variances. So hypothesis testing first. Here we are testing the variance. So we say the first group variance equal to the second group variance, all the way to the K group variance. So HO will be at least one of the variances not the same. So the test statistics here, you can see that we are using more than 2 groups. So we're going to do the same ANOVA concept. We're going to find the F stat. For our test statistics to perform, we use the F distribution table, or we can perform by using computers such as the SPSS. Then when we get the F value, then we look for the P. Again, using the computer, you can find the P from SPSS. So this is the example for Levene's test for pets and stress illustrative. So we have 3 different groups again. The variance 1 is for pets. Variance 2 is for friend. Variance 3 is for no friend, no pets. So HO they are all equal, HA means at least one of them is not equal. Then we can use the SPSS output shown below. We can find the F-stat, which is a long process. Again, we have to find the SSB, SSW, MSB, MS, and so after we find all that, we can find the F-stat. Here we are using computer, we can find the F-stat straight and get the p-value also from the F-stat. Then based on that, we can make our decision. So analyzing group with unequal variance, they say we should always stay descriptive. Use the summary statistics and also ADA, which is exploratory data analysis method to compare the groups. And also, as much as possible, we should always remove the outlines if it's appropriate. Then mathematically transform the data to compensate for heteroscedasticity, which is a long right tail that can be pulled in with a log transform. Then we use the robust non-parametric methods. So this will be the conclusion of our lectures. In short, these lectures cover the ANOVA, and anytime we want to use ANOVA, it's when we have at least 3 or more groups. Then ANOVA follow the steps of using the F-stat. In our next lectures, we're going to use a method called or non-parametric method, a non-parametric method. We have so many of them. So we're going to do a non-parametric test when we have more than 2 groups also. So again, wish everybody the best and thank you.